Hello, good morning everyone, and welcome to our presentation. My name is Hirar Daglian. I am a regional business manager from Trimble. Together with my colleagues James and Sayed, we will be doing a general introduction on Tekla software for structural engineering. To start with, this is our core messaging. We provide both structural design and design communication software specifically created to dramatically improve business performance of civil and structural engineers. We have solutions that do BIM modeling, drawings, documentation, and review. We can create LOD 500 models for steel and reinforced concrete. We also have a solution that can do structural design and analysis, code-based design and analysis, and create you all the reports according to your requirement. The solution on the left is called Tekla Structures, formerly known for its capabilities for steel, but now able to create the same level of details and accuracy for concrete also with its reinforcement. And the solutions that can do the structural design analysis are Tekla Structural Designer TSD and Tekla TEDS. My colleague James is going to start the first bit on TSD, which will be followed by Tekla Structures and TEDS. I hope you enjoyed this presentation. So the floor is yours, James.
Hello everyone, my name is James Haig. I'm an account manager for Trimble. I'm responsible for promoting our solutions to structural engineering consultants as well as general contractors here in the Middle East. For today, I'm focusing on one of our products called Tekla Structural Designer. So this is our software for code-based building analysis and design. So to give you a quick insight into the type of structures or building structures that we can design, you can see on the screen here some examples. The majority of these are buildings, so you can see multi-story concrete frames. Obviously the grey members are concrete. The blue members you can see are steel elements, and the yellow members are composite beams. You can see crucially that a combination of concrete as well as steel can be used in the same interface, and that's both framing members as well as slab items like flat slabs. You can't see any on the example here, but we can also do foundation design within the Tekla Structural Designer software. And just to give another example here, you can see a plant type structure. So the software is not limited for use on buildings only. It can also be used on industrial structures, EPC, oil and gas type structures. You can see a series of steel elements and some concrete foundations. So given the time restrictions, we're not going to be able to go through every feature available in the software. So the aim for today is to give you as engineers, civil engineers, structural engineers, an insight into what's possible with this program. So the model you can see there in my slide, this is what I'm going to try and recreate or something similar. So a few stories of concrete frame and then a steel podium on the roof with a couple of foundations at the base. So once we create the model, we'll add some load, mainly vertical loads. I'll show you the process that we go through to add wind, and then we'll generate some combinations, and I'll run the design for gravity and lateral combinations, probably notional load combinations. And then we will look at some of the analysis results, so we'll be able to interrogate the model on a global scale and an element by element scale. And from there we can look at some of the design results and generate some of the deliverables, like the reports, material quantity takeoffs, and also some of the drawings like rebar intent drawings, GA drawings, and so on. So here we've opened the software. So firstly, just to talk you through the interface, obviously the big area in the middle is where we create the structure. On the left-hand side, we have the structure window. So this is where we create a view of any part of the model. Could be in a plan view of any level, elevation view. Bottom left is an important part, which is the properties window. So this is where we control things like the meshing. When we're placing structure or elements, we control the size of the element. We can change the concrete grades, the release information, the fixity. So everything is controlled in the properties window in the bottom left. You'll see here as well, we have adopted big icons. So this is in line with other BIM type software, Tekla structures, which you will hear about or have heard about today, which is for BIM and detailing, as well as other ones on the market such as Revit. So here you can see across the top we have these different tabs. So the three ones to draw your attention to begin with. Firstly, the model. So like in other software you're using design software, we create construction levels and then we create grids at each level to build our structure. So you can see here for this model I've already set some stories of concrete as per the picture I showed you, and also the top of steel on the roof for the steel structure. Just to let you know as well, crucially, we give the level a type at this point. So that allows us to create the drawings accurately in terms of where the physical members lay out, as well as integrate well with BIM software such as Tekla Structures and Revit. So grid lines I'll come on to, but we can model steel work, so columns, column filled, encased and plated, different steel beam types, bracing, portal frames. So if you're doing industrial sheds as an example, we can model portal frames very intuitively. Concrete elements like beams, columns and walls. Different slab types, so slab on beams, flat slabs, some of them we'll touch on today, as well as composites, decks. You can add things like column drops, slab openings, slab overhangs. And then we use these roof panels and wall panels to enclose a structure, which allows us to apply load to an area through the Wind Wizard, which I'll touch on shortly. Then from a loading point of view, we have many different loading options. So you can apply loads to panels, area loads, level loads, slab loads, point loads, line loads. You can apply temperature load. Obviously in this region, we often apply changing temperature to reduce the actual force on elements. So that's possible. Also the seismic loading, so we can do seismic to UBC 97, which is the old code, as well as ACE SCE 7, which is the latest code. So all your typical loading types, all loadings that you require as engineers working in this market, we can apply in this software. Then you're into the design. So we have different design options. The first three you can see here are for steel structure. The second three are for concrete, and the third, or if you have steel and concrete. So one of the key features for our software, as I've mentioned, is the ability to do both steel and concrete in the same interface, as well as the foundations. And the options here on the right hand side are mainly for the flat slab design. So we have an intuitive approach to doing flat slab design, which I will come on to. So let's get started. So now we have the levels. To start modeling, we can start creating the grid. So you can draw in the grids manually, or you can import from DXF. So here's an example DXF that I have. As an engineer, I'm only interested in the main grid. I include it on each level, and then we can start modeling in the structure. So for me, I want to add an essential lift shaft. So to do that, I need to generate a few extra grid lines. So I'm going to create a quick one off that grid line and off that grid line. And then I can select my mesh wall command. You'll see here the properties of that wall that's going the full height of the building. You can see the thickness is 200 mil. Maybe I'm going to have a 250 mil thick wall. And then I can simply just connect the dots for the wall location. Next, I can add some columns. So if I select the column command, I actually only want it to go to the level 4. And again, you'll see mine's defaulted to a 650 diameter, but you can design for all these different shapes. To place a column, again, you just click the point. If you do a dragging box from left to right, it will select those intersections. If it's right to left, anything that box touches, it will select. So you get my columns. Next, I want to add some concrete beams. So I open a view of the level above. I choose my concrete beam command. And then if I do a dragging box, it will draw those beams along grid lines and between supports. If there's no grid line, I can simply connect the dots. Next, I want to add a slab on top of these beams. So currently it's a slab on beam. Later, I will change that to a flat slab to show you how we do flat slab design. So I choose the command. You'll see here it's defaulted to the 350 mil, which I set in the construction levels earlier. Do a dragging box, and in go my slabs. I delete my slab in the center for the lift shaft. Now I can add some steel work on the roof. So I select level 4, I choose my steel column, and then again I can just drop in some steel columns where I see fit, like so. Then Similar to the previous approach, I can add some steel beams. I can just move this here, so I can add some steel beams on the roof. And again, it'll draw them between grid lines along supports. If there's no grid line, I can just connect the dots, like so. If I hover over a member, you'll see it snaps to certain locations, like half points, third points, quarter points. If I press F2, it gives me different distances along the beam to draw in. I can add a steel deck on the roof that is, say, 150mm thick. In that goes. You can change the way these panels span. In that goes. So now we're ready to start adding some load. So firstly, I will add some vertical load. So in the load tab, you'll see here we have these load cases set as default. You can of course add additional load cases, but to start with, I'm going to add some dead load on each level of 1 kilonewton per meter squared. So that goes on each level. Then I'm going to add some imposed load on each level of, say, 3 kilonewton per meter squared. Maybe on the roof, I'm going to have 0.6 for access. If I want to add some line loads, point loads, and so on, I can come into a particular level. I can choose, say, line load. Actually, one feature that is very useful, we have this concept of shadowing the grid. And all those parts become snap points. So if I choose this option, and I want to apply some line load, maybe in areas where you have internal walls, so I can trace in some line load here, might add a point load here, maybe a patch load here. Very quick and easy to apply the loading. Another useful loading option is this perimeter load. So this is great if you have some cladding or want to apply an external perimeter load to your slab. It's great for irregular slabs. It's great against other software in that they typically have to create dummy members to apply loading to an edge of a slab. For us, it's very quick. We choose the perimeter option, we give a value, we click the slab, and it applies it around the edge. And just so you know, when we do run the analysis, the pre-analysis is it will decompose this loading via a two-way FE load decomposition. So then just to quickly show you how we apply wind load. So we have in the model tab these options for panels that I mentioned. So you surround your structure with these wind panels, and I'm not going to do the whole thing, but just to give you an idea of the approach. So you draw these panels around, and then if it's a flat panel, you choose the roof option, and then you run the wind wizard. So you see here wind wizard, and again this is a code-based input, so I run through the wind wizard. This is geometry taken from obviously the structure. The torsion cases 2 and 4 taken from the code. You can decide the exposure category. I think you choose option C for typical cladded structures in this region for each direction. Basic wind speed, let's say 55. Hit next. Then it'll work out the velocity pressures. Hit finish. And then in the wind view, if I choose the direction of the wind to be on the panel, obviously, typically you would have this whole building enclosed. Worth mentioning as well that this is a very simple building. If you have a multi-story concrete frame with irregular shaped slabs, it will be cumbersome to go around and model the panels like this. So what we do is we model these panels, but away from the structure. And then when you run the wind wizard, it will apply the wind load to the diaphragms. So that's a separate topic in itself. If people are interested in that, of course, you can contact us anytime, and I'll share my details at the end. And you can WhatsApp me or you can send me an email. But this is the wind locations as per the code. You can also generate some wind load cases. So here you can see wind load cases. So I can auto generate those as per the code. So I can pick the different directions. Do I want to include torsional load cases? Yes or no. So it's up to you which ones to select. So here are my wind load cases. Hit OK. And then I can start to look at the net pressures for that particular wind load case and those locations. And again, if you skip round, say the Y direction, I can particularly pick simply one and give me the net pressures in those locations. So that gives you a brief insight into how we apply wind loading. So now we come back to the structure. So for now, I'm just going to delete the wind load cases just to save time. We can generate some combinations. So in the combination generator, there's a few ways you can do this. You can add them manually by creating add and then dragging your load cases that are available from left to right. So you just click them across and change the strength and service factors. Or you can import from an Excel spreadsheet if you have a list of combinations that you typically use, or you can generate as per the code. So I'm going to generate as per the code, LRFD, load combinations. I'm going to choose a couple of directions for my notional loads, hit finish. And now we have some combinations ready to run. We have some gravity and some lateral, the lateral created from the notional loads as per the code. Of course, typically the wind and the seismic is the crucial, but for today it's just an insight, so we can't show that, but we can discuss if there's any specific questions on that later. So in the design tool, we have both concrete elements as well as steel elements. So I press design all. So the software runs through three types of analysis: a building analysis, FE analysis, and a grid analysis. All the loading applied gets decomposed to surrounding structure and chased down to the reactions. And then for steel work, it will automatically take the critical analysis results and calculate the steel section sizes as per the sections that you ask it to pick from. It can be European sections, US sections, whichever ones you're working with. And then for the concrete, it will work out the amount of reinforcing in the concrete as required. If you open up the show process window here, we can see the software running. So that's now completed. So you can see a few failures. So of course, as engineers, you can go and interrogate those, but most of it is passing. So now the model has been run, has been designed, we can start to interrogate the results. So firstly, I want to look at my analysis results. So in the analysis results view, I can, for any combination or load case, I can start to look at things like my support reactions in the Z direction. It's the Y direction in the Z direction. So, and you can put the text on. So here my support reaction in the Z direction. I can superimpose other results like axial force, and again put the text on. You can look at things like deflection, and then you can skip through different combinations to see how the deflection and these other results vary over time. You also have here some 2D results. So I can look at some FXY results, turn the other ones off. So here you can see some FXY results in the wall. So that's on a global scale. You can also interrogate the results on a member by member scale. So I can ask it to show me the load analysis view, member view. Actually, the analysis view I want. Open analysis view. So here you can see the size of the element, the shear force, the deflection, and the moment. So that's some analysis results. Then you're into design results. So back here, the first view you can see, as we saw earlier, is the status. Is it passing? Is it failing? Is there a warning? You can also look at the ratio, so you can see how hard the members are working on a color coordinated. If it's green, it's about 0.4. If it's yellow, it's working a bit harder. Orange, a bit harder, and so on. You can also interactively look at things like the fixities. So I can see if it's green in this view, then it's fixed. If it's yellow, then it's pinned, as we like with concrete members, it's fixed. Steel members are pinned. Also the material sections that have been used. So you can see we have one floor of steel sections. This is a color coordinated view of which sections are being used for the steel work. So now let's say I want to make a change. Currently we have a slab on beam structure. I might want to say the top floor, I want to change to a flat slab. So very quick and easy to do that. In the model view, firstly, I make it unique. And then on the top level, there's two steps to turn this to a flat slab. Number one, delete the concrete beams. Number two, turn the slab type. So I say the concrete slab type from a slab on beam to a flat slab in the properties window. One thing I've not mentioned, we have this button here called the validation. So this checks model connectivity. I can see I have some warnings here. Discontinuous member supported by the building. The slab must be enmeshed in 3D. So yeah, so with a flat slab here, there's nowhere currently, because of the way this slab is meshed, for this force from this column to decompose into this slab. So what I need to do is, at level 4, I need to mesh two-way slabs in the 3D. Now when I rerun the design, it should redesign and reapportion that loading to the slab, which then gets decomposed. So now we have a failure here. One thing to mention is the way my software runs is when I hit design, it will automatically design everything. The second time I hit design, the steelwork is now defaulted to a checking mode. Concrete stays in design. So I should be able to now right click on this member and ask it to redesign me that member. And that's now passing. So if we now look at the slab here, we can start to interrogate the wood armor moments in this slab. So again, I come to the results view, I choose analysis type, I choose a combination, and I want to look at my wood armor moments or moments in the DX. In that direction, I can look at it in the bottom, or in the top in the Y direction, and so on. So our approach to slab design, we use a similar approach to one you're familiar with regards to creating result strips. I believe in SAFE and other solutions you create the result strips manually. So here we have the option, you can create them manually. But we're trying to automate that approach. So we have this concept called patching. So patching is a concept where we create the result strips automatically at 1 meter centers in both directions for certain situations. So you can patch columns, you can patch walls, you can patch beams. If you have a transfer structure, you can patch areas of the panel. So if I choose to patch columns, I can draw in a dragging box, and it will create these patches at column locations where we have high moments. Same goes for walls, so I can create a patch for the wall, like so. You can change the size of these patches. I can drag the size of the patch out, like so. And then I can look at the results in those patches. So in the results section here, if I turn off those results and look at strip results, you'll see here how we have the results for deflection as per the strips in the columns and the walls. Same for the moments, and again you can put on the text. If you hover over a particular result strip, you can then see the results for the shear, the moment, the design moment, deflection, errors still required, and so on. So what that allows us to then do is in the design tab, we can hit design slabs, so it automatically works out the reinforcing required in the slab areas, ignoring the higher areas of moment that we get around column heads. So if we then hover over a particular slab, you can see here that we have the reinforcing that it's worked out, top and bottom in both directions, T12 is 150 sensors. I can also show you the results for these. So check panel. So here we have a summary table, and this is something that's very powerful with the software, is the transparency and the presentation of the design checks. So this is the first one I've shown you for today. This is for the slab, obviously. Summary table is there. I can then drill in and I can look at each direction of reinforcing the calculation that's been worked out. Then I can hit design patches. So what it does is it takes the normal reinforcing in the slab and it adds additional reinforcing as per the required moment in the strip. So if I hover over it, you'll see there X left, X center, X right, Y left, Y center, Y right. And again, if I check member, check slab patch, I can see in this summary table the strip, the amount of reinforcing taken from the slab, from the nominal reinforcing, added reinforcing as per each strip to give me a total area of steel provided versus what's required, and then a utilization below 1, it passes. And then just quickly back to the structure here, if we look at some other design results. So as an example, if I want to look at the results on my steel, I can right click, check member static. So here is again the summary table for that particular element check. These are all your design conditions or checks as per the code, the values, the capacities and so on. And again, if you click into any check on the left, it will explode out the critical combination, critical span and critical location. And then it gives you the calculation it's doing. Any reference to the code, like a coefficient or a factor, it tells you whereabouts in the code it's got those from. And it's the same principle for the beams. So I check the beam, concrete beam. Here we have 3 spans. You can see the 3 spans, and again it will show me initially or straight away the critical. So it's the critical check is this particular span, this section, this bar, this location. So again, you click in a particular span, it explodes out the longitudinal bar check, the location, the analysis, and the combination. And again, with these little arrows on the side, you can press these and it will actually explode out the calculation that the software is doing. So very transparent, very easy to see what design process the software is going through. So then we're just into some deliverables. So I can generate some drawings from the drawing tab. As examples, I'll create some concrete beam detail of, say, all the beams in the model. So here are all the beams in the model. Hit view drawing. While that's loading, I'll also show you a general arrangement drawing of, say, the roof structure, which is, say, level 5. So you drag it, whichever one you want to show, hit view drawing. And again, these open up in AutoCAD specifically. So as the first one, here are all the beams in the model. You can see here an elevation view of the beam, lap lengths, curtailment lengths, dimension information. You see a section view through the beam, and that's for all the beams in the model. And then on the right hand side, you'll see a table summary of the reinforcing used, so different types, the masses, the lengths, to give you a total mass. This is all to a different layering standard and scale that you can control. Obviously with this one I've set up the colours quite nicely, you can see different colours involved. For this one I probably need to update it, it's currently all in green, but you can see the member reference, the section. If it was a composite beam, it'd have the number of shear studs in it, you see the slab thickness and the slab type used here. So that's some examples of some drawing deliverables. Also things like schedules, so I can say level 1 I want to create a beam schedule. Again, a few clicks. Here's my beam schedule with all the information, the marks, the sizes, the bottom bars, top bars, stirrups, and so on. So I realise I'm going through this quickly, but I only have 15 minutes and I might have gone over that. Hopefully it's not too frowned upon. Last thing to show you before I finish for this very brief summary is the foundations. So in the base, let's say I want to add some foundations. I go to the foundation tab. You define your piles in the catalog. So it doesn't design the piles, but you define the pile properties, like the reaction in both directions, installation type, the shape, what's the capacity, resistances in both directions, and so on. But then I can create some certain things, like I can create like pile caps or pad footings, say pad base, like so. Maybe in this area I want to create a raft footing, so I choose my rectangular option. Again, I'm going to change the properties here. Let's say it's going to be a 1 meter thick raft. The allowable bearing pressure is going to be, say, 350. You can control the spring stiffness or subulus or modulus of subgrade reaction, I think you call it in SAFE. So you can control that. And then I can just draw in my slab. Okay. So I'm going to delete the supports. Quick validation, okay, that's fine. Now if we look back to the structure, I should be able to, in the foundations tab, I can hit design pads. So it automatically sizes the pad, length, width, depth, and utilization. Also the reinforcing, so I can check the member. So here's the applied load summary. Bearing capacity check is the critical, but it does all the check for foundation design. So bending capacity, shear capacity, pointing shear, sliding, uplift, and so on. Same for pile caps. So design pile cap. So it can design between 2 and 3 pile caps. And again, if I check that member, you'll see the pile capacity check, bending shear check, pile one-way shear, and so on. Then for the raft, I can click design rafts. So first I need to rerun the overall design because we've now changed the stiffness of the overall project. Now we've removed those supports from the base of those columns. So we rerun that so we get the right loading at the base of the columns into the slab. And then we should be able to design the raft. So then foundations, design mats. So here we can get a failure. So if we can right click, we can ask it to check panel. So I can see here that bottom X and bottom Y, we can't fit enough reinforcing in, but only by about 6 or 7% is it failing. So maybe as a quick step, you might make this a bit bigger, say 1,100 millimeters, sorry, 1.1 meters. And then redesign the map. Is that now passing? And then lastly, just quickly, you can create some quick fire drawings. So as an example, here we have our flat slab with reinforcing and nominal reinforcing plus additional reinforcing in the strips. In the draw tab, we have these quick fire drawings you can see. So I can create a quick slab mat detailed drawing. Again, open straight up in AutoCAD. So here you can see the reinforcing top and bottom, both directions, the slab thickness, the reinforcing in the actual strips, and again the reinforcing types, masses and lengths on the right hand side. Same goes for things like the foundation layout. Click of a button, there's my foundation layout, my slab thickness, my wall information, power cap information, and then the reinforcing arrangement in the power cap and the pad base, as well as the schedule for the footings and so on. So that concludes the presentation from me. I've gone through it very quickly. Hopefully it's given you an insight. Hopefully you're excited by this technology. It is very intuitive, very quick, and I'd be happy to discuss with you anytime this software. So yeah, thank you, and hope you enjoy the rest of the PICE seminar.
This is the Tekla structures interface. You see the ribbon interface. We can do the model in multiple ways. We can start from scratch by choosing commands like the footing, like the column. See how easily we can place them, and then a beam. All these elements are parametric. They all have predefined profiles, but we can also change them. You can see the window here, how we can define profiles according to our requirements and then save them, or everything is customizable. The other thing that we'd like to draw your attention here is that whenever you click on an element, you see all the values, all the attributes, the weight, the size. And if you change the parametric element, the values also change automatically. Even if you can select multiple items, this will also allow you to see the values changing according to your selection. Another example of how you can start modeling is by importing from an Excel sheet. If you see the video here, we have a lot of piles. When we look at the sections, we see them with different sizes, length, and starting points. If you model them manually, it will take a lot of time. But if we have an Excel sheet with the information, we can just import it easily. We can just choose the file and just press import. It will be imported automatically within a second. This is a second way of generating a model in Tekla. A third way is also if we have a PDF drawing or a CAD drawing without a model, we can import it also easily if you see all the options available. Uh, you can open the PDF drawing, import it. Uh, we start the origin point. It will be imported to the model. What we need to do after importing the PDF drawing is to update the scale. We can just select the drawing. We have a nice tool called reference model scale. We just choose one dimension in the PDF drawing and we type that dimension manually in the box that appears. In this case, it's 2150. Once we enter the value here, it will automatically scale up the drawing one to one. This will help us to use the drawing as a reference to place our elements in 3D on top of it. Uh, in one step, we can just choose for example, the footing, then the column. If the dimensions need to be changed, we can change them easily. If you see on the right-hand menu. And then we can rotate also very quick, very easy. As I said, these elements are all parametric. We can also drag and drop, visually change their dimensions, all the information change automatically. Um, this gives us a very flexible way of modeling. In case we have a 3D model, let's say we have a Revit model, which is the most rich information model possible, since it can be converted to IFC. We can ask the whoever modeled the Revit is to give us an IFC, a converted IFC. We can import it directly to our model. We can just double click on it and choose the origin location. It takes seconds to import. This is a reference model, which is a geometry model. But if we need to work on it in Tekla and add reinforcement, we need to convert these elements into native Tekla elements. How to do that? We have a tool to do that. We can just go to Manage, Convert IFC Objects, choose the elements that we need to convert. It will also automatically convert them. After the conversion is done, these elements are now Tekla native elements that we can work on in Tekla, and we can reinforce them, and we can do whatever we would like to do with them in Tekla. All the properties, all the information is carried out from the IFC. Let's say the IFC model is changed, the Revit model is changed. We also can manage the changes. We can import the revision model to the same file. Uh, we just, let's say, import the second version, and then we have two versions of the same model at the same time in the Tekla model. Then we have something very nice here called change management tool. We choose it. This shows us what has changed. The green ones did not change. The red ones are deleted. The yellow ones are changed. We can easily see and track the changes. Whenever we press on a line, it takes us automatically to the areas. Very easy to track. The zoom in is automatically done once you press on the item. So we have now a changed IFC model, which is also changed, imported to Tekla and converted to Tekla native elements. We can work on it easily. And even if we have reinforced our initial model and the reference model, in this case, the Revit model is changed, then upon changing it in Tekla, the reinforcement will follow those changes. So we don't have to start things from scratch. We just need to follow the changes and manage it easily. As you see, some columns have changed in their dimension. And as I said, if we would have put reinforcement there, the reinforcement would have followed the changes. Now, how to do the reinforcement? We have multiple ways of doing reinforcement in Tekla. This is what we're very strong and proud of. We have the rebar sets, we have the rebar groups, but the nicest way is these applications that we have that are predefined for repetitive complete element. Let's say we have a footing here that we want to reinforce. We just choose the right application on the right side. We double click on the element and it is reinforced automatically with all the layers. When we double click on the component, it will just show us all the details, the primary top bars, secondary top bars, and all are customizable. All values can change, and the model will be updated automatically. Even the names of the attributes can be changed. Again, even if the element is changed, some dimensions have changed, the reinforcement will follow it. So this is a parametric way of reinforcing the concrete, which will save a lot of time, especially under repeats and revisions. And the same way, we can reinforce the other elements. Uh, Here is an example of how to reinforce the starter bars. Again, with a click of a button, it's reinforced on the start of the column. Again, we can modify the options and the parameters easily whenever we place on the item. If we go to the columns, the continuation, it's also a click of a button. We can reinforce a column easily using the rectangular column reinforcement application that we have. Again, we just wanted to show you how we can modify the sidebars, the stirrups, the intensity of it. These all key change the spacings, and the intermediate links can be controlled easily here according to the design intent. On the same way, um, we can reinforce a strip footing. Uh, as you see again, it's reinforced automatically, and so on. All can be go on simple elements. Let's go to a very more complicated element. Let's say we have this big slab with these complicated openings on top, and we want to be to reinforce it. This can be reinforced manually, but it will take a lot of time. We have a beautiful tool here called reinforcement mesh, and it will save us 90% of the time that we take to reinforce it. Mesh bars are shown on the right side. We click on it, and then we click on the element, the slab in this case, which is also easy to control and easy to edit. The auto mesh item is used for big complicated slabs. After setting up all the parameters that we need on the rebar groups and the splicings, we can just uh, click on the slab that we want to reinforce, and it will do it in a couple of seconds, maybe less than a minute in this case, because it's a very big slab. As you see, the slab is reinforced now. We can check on the cross section here how things are done, the details, all done, all can be seen. All openings are followed here. All top and bottom reinforcement is done according to the standards. All the lab splices are followed according to the standards. If we want to do the bar bending schedule, all we need to do is do the numbering. We number the reinforcement. All similar rebar marks are being grouped, and this is all done automatically. And once we want to create the bar bending schedule, it's a report. We have the formats predefined, many types of formats. In this case, we will just use the standard one, rebar BBS in A4 PDF format. Of course, these are all customizable according to the requirements that we have. Once we choose the report type that we need, it's populated automatically with all informations and figures of our shapes shown on the schedule. And at the end of the uh, report, we have the weight summary by bar size. This just shows us the total weight and total number of bars, which helps on the cost estimation, an accurate cost estimation. Once we want to create a GA drawing, for example, we just open it from the general arrangement drawing properties. We choose the properties of the drawing, the title block that can also be predefined from the beginning, and we just press OK, and it is created. This is just the customization that we have prepared initially. You see the title block on the right side, and even the bar bending schedule on the upper right side. These all can be customized. The placing can be changed. If we go to the reinforcement, this is the slab that we have reinforced. We can just add the dimensions the way we want. This saves a lot of time, as we don't need to double check the information. All dimensions can be run automatically. We can just put the rebar marks, and it will be populated on the drawing. This is how the reinforcement marks are done. If we zoom in, we can see all the values are put automatically, and all these annotations actually can be customized accordingly. The position, the font size, the placement, the color, all these CAD attributes actually can be automated and customized one time, and then all projects can be followed accordingly once we choose it.
Tekla Text is a design software for repetitive calculations. The aim of this is to replace your hand calculations with a very powerful, sophisticated calculation tools, which has got there are two instances here. That's a text for a library of calculations, where you have at hand lots of calculations which you can use directly by giving the inputs. Then you have got an empty text forward document where you can write your own calculations and add it to your standard calculation chart. So I'll be showing you text for the library for text, and I can open one project in here which I've done. There, that's basically how this is set up, and you have got different environments which you can use: the UK, US, European, and in this settings, you can see that you can work in any environment and follow the either the SI units, or you can use the imperial units from as well if you're using the US locale. So with this overview, you can see that I have got some readily done calculations for steel beams or column base plates, where you are giving some inputs, the forces, and it gives the complete calculations. Similarly for the column base plate, there you go. So this way, there's another sample of a retaining wall, and you have got all the calculations in there. Stability checks for overturning, bearing pressure checks, moments on and horizontal forces, vertical forces on walls, reinforcements, and so on and so forth. So all these checks are done to give you a complete calculation table that can be presented to the client for consultant for approval. So these type of calculations are there. I'll show you one document, and if I open a new document here, you can see all the type of available calculations which are there, for whether they are for concrete, for steel, or for any other material calculations you can find in here. So the foundations as well, you can see that we have got the foundations as well. If I go in and show you, want to show you the pad footing analysis and design and do the calculations, I've got a new sheet basically for pad footing analysis and design. That's the sketch basically for the input properties. You can give the dimensions, length and width of the pad foundation, number of columns which are on there, and such as loads you could give some dead and imposed such as loads on, and also the soil details. You can see that we've got different soil details, and if you would want to give, say, some input parameters and properties. Okay. Finally, if I want to add the loading, and let's say the size of column is 400 mm by 400 mm, you can see that this is interactive. Once I change the values, that's also going in there. We now give some loadings in here for axial loads, horizontal loads or moment, Okay, if I have to give some values in here, the total horizontal loads are calculated in x and y direction, uh, and then moments in x and y as well. So I'm giving some input, some values in here, and once I'm done, I go in. So you can see that it gives me a summary, and there is there was a warning there for the base reaction. However, I'm just trying to give you an overview how this works. So based on the input values and loadings, it does the checks for stability against sliding and overturning in the directions where we have given the loadings and moments. So basically, these calculations are done, and that's how Tekla works. Uh, so if you can go in and yeah, not the, another document. There are some steel connections as well. So you can go in at create a beam analysis and design, just simple beam analysis and design. You could do it. Okay, the beam geometry is there. Length is 8 meters, and you've got the beam and loadings. You can add some loads in here. Okay, and also the loads, let's say 10 kilonewton per meter full UDL, and also generate the combinations. Uh, and yeah, so once this is done, then I get the complete calculations for this beam as you go. So that's the Tekla text which I have to show. Thank you very much for attending this session. I'll pass it on to Harayar for for his inputs. Thank you.